Okay, the handout I gave you is called the common ion chart, and this is my common ion chart. It varies. This common means someone said this is common. That's how we ended up with a common ion chart. Depending on what class you take next, you may have to memorize some of these ions. Whether you're going to take 2A next or 1A next or 3A next. It'll vary. Okay. For my class, I want you to be able to use this common ion chart, not memorize it. This will be available on your next test also. You don't have to worry about that, along with the periodic table that you can actually read. All right. Speaking of that, I'll have the test done actually tomorrow. So, and if some of you would like to know your test score earlier, email me and I'll grade yours first. For those who don't want to know, don't send. Yeah. All right, so let's get going here. Now, there are 3 types of namings we're going to have. We're going to have ionic compounds, covalent or molecular compounds, and acids. Now, we're not going to talk about acids until we get to the chapter on acids and bases. So in your dry lab, when you want to run across a acid, skip it. I'm going to give you the 5 acids that are most commonly used. You'll see those. And then we'll go into more depth when we get into the acid-base chapter. Okay, so let's cover the acids first here. Okay, let's do one more. Okay, so we have the 3 strong acids. And we'll talk about what do I mean by strong versus weak acid when we get to the last unit. Hydrochloric acid, that's commonly used in pools. Muriatic acid is usually what it's called when you go buy it at the pool store. That's the same kind of acid that's in your stomach as well. Sulfuric acid is a very powerful acid as well as nitric acid. Sulfuric acid you use a fair amount in organic chemistry. The weak acids, acetic acid, which is vinegar, and then phosphoric acid. Phosphoric acid is used a lot in organic as well. Yeah. Nitric. Now, I have an interesting story about acids. Who's seen Breaking Bad? Okay. Remember when the tub fell through the floor? Remember what was in the tub besides the body? What kind of acid? No. Hydrofluoric, HF. Now, that stuff is really awful. It will eat flesh quite nicely. It'll go through clothes quite nicely. And it's not considered a strong acid either. That's lye, which is a base, not an acid. And in organic, you usually make soap also. It's very easy to make. Lye soap is, ivory soap, very easy to make. Okay. In fact, we're doing that in 2 weeks in my other class, my organic class. Okay, so I had a student who was retired out of the Coast Guard, and his job in the Coast Guard was as an inspector of container ships. He had to go through and he would randomly pick like 150 or 200 containers and inspect it. And he had to wear a hazmat suit. Now, a hazmat suit is a hazardous materials suit to protect him from hazardous materials. He walked into one container and he noticed a spot on his sleeve. And he noticed flesh underneath the spot on his sleeve. And he also noticed there was bone there. And he looked up and there was a hole in the top of the container. Containers are made out of steel now. And he could look all the way up. Well, about 5, 6 containers up, there was some leaking hydrofluoric acid, HF. Came all the way down, and he had a massive scar on his arm from that. So HF is, I can see where I can't imagine getting a tub full of this stuff. And you have to put it in glass. You can't put it in plastic because it'll eat through the plastic. Yeah, it's really bad stuff. Okay, so those are the acids you're going to run across today in your dry lab. So you can either name them if you want or skip them. We'll be covering those in depth in chapter on acids and bases. All right. As a review, you do need to know the periodic tables, metals versus non-metals. As a definition of an ionic compound is the combination of a metal plus a non-metal. So you have to know what a metal is, what a non-metal is. All right. So we are going to name 2 kinds of compounds. Covalent naming. Sometimes this is called molecular. Let me write this down. In fact, I think your dry lab uses the term molecular versus covalent. You'll see them interchanged. All right. So you have to be able to identify your compound as, is this a molecular compound or is this an ionic compound? How do you tell? Okay. Okay, there are 2 ways of identifying an ionic compound. One is you have to have a cation and an anion. Okay, you have to have both, no exceptions. In other words, a positive ion, negative ion, no exceptions. Sometimes they're defined as a metal plus a non-metal. Now, metals usually form cations. Non-metals usually form anions. That's why you'll see that one used as much. Okay, so that's when your chart comes in handy, because it's divided into cations and anions. So you look on the left to find a cation. You look on the right to find an anion. A covalent or molecular compound is usually made up of non-ions or or just two anions? So let me give some examples here. Let's look at good old table salt, sodium chloride. Is that ionic or molecular? Well, where is sodium on the periodic table? Right here on the left. Chloride is on the right. We have a metal and a non-metal. So is that an ionic compound? Yeah. It also is a cation forms a +1, and an anion it forms a -1. I did click on recording, right? Oh yeah, right there. There's a recording thing. So sodium chloride is definitely ionic. What about chlorine gas? Ionic or covalent? It's covalent because it doesn't have a cation there. Cl is an anion, -1 when it's an ion, but you don't have the cation to match it. So it's covalent. What about that? P2O7. Okay, look on your ion chart. Find P. Okay. Now, does it have a cation? P is on the right in the non-ion or the non-metal, right up here. P is underneath nitrogen. Nitrogen forms a -3 anion. So because P is underneath N, P forms a -3 ion as well. Okay, so that's the way to identify whether you're looking at a
Blinding yourself.
yeah, doing a good job of it too. Um, C for covalent or I for ionic. So that's the first step you have to be able to do is identify what you're working with or whether it's an acid or not. I'll show you how to identify. Acids basically are a compound that can disassociate a hydrogen ion, H plus. If it can disassociate, it's an acid. Some are strong, some are weak. Okay, so step number 1 is covalent or ionic, molecular or ionic. Then you use the appropriate naming conventions for each. They aren't the same. Now, these are binary compounds. What does binary mean? 2 in 2 parts. All of them we're doing in dry lab binary compounds, including acids, binary compounds. All right, between the two, most students find covalent naming easier than ionic naming. So we're going to do it first. Now, on your chart I gave you, I want you to notice a few things. oxoanions. Think of it as think of it as two words, oxoanions. And you know both of them. You just put them together. Yeah, words you use every day, right? Okay. So notice it says on the top right over here, covalent. We're going to be using these names for how many of something. Mono, di, tri. Okay. On down the list. You need to, now you're going to have this on your test, but these you should feel comfortable with doing. Probably, you know, mono, di, tri. You probably know penta and hexa, octa, and you probably know deca as well. Some of them you probably haven't heard of is nona. Nona is 9, hepta is 7, tetra is 4. Those are 3 that you probably aren't familiar with. Those others you probably have heard some way or another. Okay, so let's go back to our naming compounds here now. I'm going to name covalent. So we're going to be using this covalent chart now. Okay, so binary. We've established that's 2. So binary naming of molecular or covalent compounds is in 2 parts. Ionic is going to be in 2 parts also. So this one, the first word is from just as it appears in the periodic table. So let's name P2O7. Okay, so from the periodic table, P stands for what? Phosphorus. The second one is an ide, IDE. So it could be oxide, phosphide, nitride, hydride, okay, which is on your common ion chart, upper right. So it's going to be these guys, the ides. Okay, so we had O, so that's oxide. Okay, so step number 1 is to identify the name from the periodic table and then an oxide in that common ion chart I gave you top right. Okay, the second step, well, the first step really is to identify is this ionic or covalent, I guess. And then when you get into the actual naming convention, that's when step 1 is phosphorus oxide. Okay, the second step of that naming convention is how many. So how many do we have here? 2. So that means that is a di. And how many is this? 7, so it's hepta. So that's diphosphorus heptoxide. And this is pronounced as an O. Okay, so diphosphorus heptoxide. So, ionic or covalent? If it's covalent, we get into the covalent naming convention. First step is to name the two parts. And the second part is you look at the numbers there. How many? And use that top right naming scheme of mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And as you use these, they'll become more and more familiar. When you get into organic chemistry, now some of you are going to have to take OChem. When you get into organic chemistry, these will be extremely common. You can recite these in your sleep once you get into OChem, because you're going to be using them like every day. So, all right, so let's do another example here. Let's do a really common chemical. Let's name that, besides calling it water, let's name it as a binary compound. Number one, is it covalent or ionic? Now, H is always an anion, H minus one, except when it's an acid. But water, not an acid per se. Keep that for another time. Okay, so is this covalent or ionic? Covalent, because it's on both the H and the O is on the top right side of that common periodic table, and also on your common ion chart. Okay, so we have to name it using the binary convention. So hydrogen from the periodic table. Oxide. How many hydrogens? 2. How many oxygens? So it's dihydrogen monoxide. So we have 2 vowels together in the middle there. We're going to eliminate one of them. Now, most people are okay with the covalent molecular convention. It's the most straightforward. Most people are comfortable with it. Okay, let's tackle the ionic one now. The ionic one is different. Still in 2 parts, but there's no mono, di, tri part to it. You balanced it out with charges, because ionic compounds have charges, pluses or minuses. And you can't have an isolated charge in nature. It's got to be neutral. So that's what's going to drive the numbers. Well, let me add one more thing to the covalent. The issue of mono. One is a weird, like, what is that? 5, right? Do you ever write a 1 superscript? Who in here writes the 1 superscript? Gosh, no one's raising their hand. What a surprise. That's because it's assumed. When we're writing covalent equations, there's some assumptions there as well. The problem is it varies. So notice here with the water, I put in the mono. If it's on the second one, on the ide side, it's required. On the left one, it's optional. So if we had PO, let's name that. Okay, so we have 1 phosphorus. So we can use mono or we can leave it off because it's on the left side now. Your left, okay? The oxide has to be there. So that's required. So it's phosphorus monoxide or monophosphorus monoxide. Now, some people don't like options. They just say, if I put on mono on everything, is it going to be right? Yes, it'll be fine. But in the beginning, it is optional. Okay. So you can put it there if you want, but the second one has to be there. No exceptions. Okay, so let's go on. Does that make sense? Very reasonable. Okay, so let's now go on to ionic. Of course, step number one is this ionic or molecular. Okay, with ionic, charge balance is required. No exceptions. And what I mean by that is the positives have to equal the negatives so that there's a net charge of 0. So let's look at sodium sulfate. Now, when you're naming compounds, you need to go from the name to the formula, formula to the name. Back and forth. Same with the ionic. Name, formula, formula, name. Okay, so sodium sulfate. Find sodium on your common ion chart. Did you get one? Where's the stack of handouts? Are they still floating around? Is it somewhere up there? I made 44 of them and there's only. Yeah, just pass them on down somehow. I want you to meet them halfway. Okay, everyone have a common ion chart? Okay, I have an electronic version of this on Canvas. You go to Files. I also have some worksheets there. So you're going to have your dry lab plus my worksheets as practice. And you need to practice this a fair amount. That's one of the weak areas of incoming 1A students and 2A students and 3A students. Naming. Naming is very weak. So I want to give you guys plenty of practice. Okay, so how do I write sodium? Na. And to start with, put the charge down. Na plus or Na plus 1, whatever you like. What about sulfate? What's the formula for sulfate and its charge? Look on the right and kind of in the middle. Exactly. Now, SO4 as a group, 1 sulfur, 4 oxygens as a group have a charge of -2. The whole thing. Think of parentheses. Okay. All right. So we have one positive and two negatives. What's wrong with that? How many positives do we need? Two. So the formula for sodium sulfate is Na2SO4. Now there's a mandate here. It's required to have the positives and negatives be equal. So the net charge is 0. No exceptions, okay? That's nice when you say no exceptions. As opposed to, well, sometimes you do this, sometimes you do that. This way it's easy, no exceptions. Okay, does everyone make sense why we have to have two sodiums? Okay, notice in the name sodium sulfate, what's missing compared to the covalent naming? Exactly, perfect. There's no di. There's no disodium sulfate because it's ionic. So the only time we use the monodi if it's covalent or molecular. Only time. Because the charge balancing is where the numbers come in because of the charges. Okay, now going back to covalent for a minute. If you see a di, tri, or mono in the name, it's automatically covalent because ionic is not allowed. So you automatically think covalent when you see the mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca in there. Automatically covalent. Now that doesn't mean it's not necessarily that, but automatically it's covalent. Okay. All right. So let's do another example for ionic. Okay, aluminum sulfate. What's the formula for it? Okay. What's the aluminum? Al plus 3. Now you can write 3 plus or plus 3, either way is fine. And what's the charge in sulfate? That's -2. Okay. So is this formula balanced? AlSO4? Well, how many positives do we have? 3. How many negatives? 2. How do we deal with this? If you're adding 1/2 and 1/3, is the answer 1/5 or 2? No, what is it? What do you have to do first? You have to find a common denominator by multiplying 2 times 3. What's the common denominator? What's the common denominator with 2 and 3? 6. Okay. So how many 3s are in 6? How many 2s are in 6? And now I have to use the parentheses. So the formula without the charges is Al2SO4 3. So write the charges first, unless you've already done this before in another life. If you've never done this before, write the charges and then rewrite it without the charges. Because with the charges in there, when you go back, you'll understand why you did it a certain way. All right. Does that make sense? Al2SO4 3. Um, now, our world, our world, well, let me tell you a story. Back in 1985, we voted in a president who decided that the metric system was not for us. And the previous president spent about $150 million educating the United States to the metric system. We put kilometers per hour of street signs, the cars come with kilometers per hour and miles per, all that stuff was done during the early 80s. This new president came in and said, poppycock, that's ridiculous. Everything in this world revolves around the United States. If we say pounds, it's going to be pounds, not kilograms. Well, there are 7 countries in the world that use the imperial system, and we're one of them. 5 of those 7 are tiny little countries that are dominated by the UK. Yeah, what does that tell you, right? So anyway, in a similar situation, back about, probably 80, 90 years ago, there was some confusion in naming cations. So let's look at that confusion, and I'll show you how things have gotten complicated. Now, certain transition metals, those metals in this middle piece here, have multiple charges. And it's an issue with stability. That's what I'm going to cover tomorrow's video. And over the years, we've developed these names for them. And unfortunately, there's no consistency. For example, iron 2, positive 2, is called ferrous. Iron positive 3 is called ferric. And this 80, 90 years ago, he said, that's so confusing. Let's call iron positive 2 just iron 2. So that refers to the charge. Now that's very nice. But if you look on a food label today, 2023, you're not going to see iron 2. You're going to see ferrous oxide, ferrous chloride, whatever. So iron 3, positive charge of 3, or ferric. Now, ferric compounds are very common. One of the most common one is ferric oxide, which is rust. Lead. Lead 2, that means it's a Pb plus 2, or plumbous. Now the OSU and the ick are related. The us is always less than the ick. So if the ick is 3, the us is going to be something smaller than that. Not necessarily 2, it could be a 1. And this inconsistency, because here the ick refers to positive 4. Where up here, the ick refers to positive 3. So it's not consistent. However, what is consistent is lead 2 and lead 4. There are no exceptions here. Whenever you see a Roman numeral in the parentheses, that is a charge. And it's always positive because it's a cation in the transition metals there. Okay, so when you look on food, they'll be using the old word. When you look in, if you buy a pesticide and look at what's there, it'll use the old word. When you look on your prescription drug, it'll use the old world. Now, if you're an analytical chemist in our department here and you order online some chemicals, they're going to use iron 3, iron 2. So you need to know you'll see either one. And this department has chosen not to teach the ferrous and the ferric. I have chosen to show that to you because that's what you see in real life. That's what my middle name is. That's what the R stands for. Okay. All right. So if we see ferric oxide, also known as rust. What is the formula for ferric oxide? Well, ferric. You look on left side of your common ion chart. It's Fe plus 3. Oxide on the right side is going to be O minus 2. So do these balance out? This is a 3 and the 2, just like the aluminum sulfate. So whenever you get to 3 and 2, I want you to think 6. So how many 3s are in 6? 2. How many 2s in 6? 3. So that's the formula for rust. Ferric oxide. Now another way to name this would be iron 3 oxide. Now, the next week we're in the lab again. You know, we have all those bottles of chemicals around the edge of the lab. Start looking at the labels they use. Sometimes they use the Roman numeral 3. Most of the time they do actually in there. Other times it's ferric. Now at Sac City, there was a lab write-up that called for ferric nitrate. Ferric nitrate. And no one could find it. All they found was iron 3 nitrate. And they did not know that ferric and iron 3 were the same thing. And their lab and the chemicals needed to be switched up so that they agreed with one another. All right, what's the formula for ferric nitrate? Well, we already know ferric is Fe plus 3. Nitrate is, what's nitrate? Yep, NO3 minus. So what's the formula for ferric nitrate? How many of those NO3s do we need? 3. So the formula is FeNO3 ferric nitrate. Ferrous nitrate is going to be FeNO3 2. because ferrous is a +2 iron, or iron 2 nitrate. So on the left side of your common ion chart, you'll see a fair number of dual names. Now, these are common ions. There are also ions that are not on this chart. For example, what's the charge on beryllium? Beryllium is second column in, so it's an alpha alkali earth metal. What's the charge on alkali earth metals? +2. Notice beryllium is not on there because beryllium is in the group of alkali earth metals, which are all +2. So keep that in mind. If you can't find something on this chart, look on your periodic table. The periodic table will always be your friend. Okay, let's do a few more examples, then I'm going to start our dry lab. Okay, aluminum acetate. What would the formula for that be? How would I write it? Yes, I was just about to talk about that. Okay, notice on the bottom right, acetates up towards the bottom. I have it written two ways, and they're both correct. Unfortunately, if you're an organic chemist, you write it the top way, and if you're an inorganic chemist, you write it the bottom way. Same with formate on the right. Formate organic, formate inorganic. Same formula. The top one connotes structure. The bottom one doesn't. The bottom one just says how many of each you got. How many C's, H's, and O's do you have? The top one says which ones are acidic, which ones are not acidic. Okay, so aluminum acetate. Where did it go? No. Aluminum acetate. So aluminum is Al +3. What's the charge on acetate? -1. So we need 3 of those acetates to balance out that 1 + 3. So aluminum acetate is Al CH3COO parentheses 3. Okay. Now, if you should see the formula, what is that chemical? Remember, it's always in 2 parts. So aluminum, and what is COO? Formate. So this is aluminum. Aluminum formate. There's an acid called formic acid. Formic acid has an interesting story as well. Formic acid was discovered by a mean little boy. He decided that red ants he didn't like, so he decided to collect a whole bunch of them and boil them in water. And his dad was a chemist and wanted to figure out what was in that water after his son so cleverly boiled them all. And he discovered formic acid. And when a red ant bites you and it stings, that's what they're injecting into you, formic acid. Okay, so yeah, he's the same one with the magnifying glass on the ant pollen. Yeah. Okay. This is what your dry lab is all about. It's just practicing this. And don't forget, you go to Canvas files, unit 2, you'll see I have a whole bunch of worksheets towards the bottom of the list. Some are naming covalent, some are naming ionic, some are mixed. And you need lots of practice. Now, in your next test, there's going to be a fair number of these, so just be forewarned. And the reason why there'll be a fair number is because that's one of the major weaknesses of incoming 1A, 2A, and 3A students. Yeah. Well, there's this one that I'm going to end right now. Also, a guy named Tyler DeWitt